Hello, George Notchik here. Today is Monday, April 8th, 2019. This is another update on the barrel curvature test on the ice. Things are not looking good. Haven't had very good weather. Yesterday it was misty and then turned into heavy fog. Today the fog blew off, but it's up around 41 Fahrenheit at the moment with 98% relative humidity. Now it's supposed to cool down tonight below freezing, so there's a chance that this is going to work tomorrow morning or the next following 2 days, because it's going to be below freezing overnight time. Not a whole lot below freezing, maybe about 3 degrees Celsius below freezing, but it should be enough to precipitate out a lot of the moisture out of the air and clear up the air if we don't have any rain. So keep our fingers crossed that we're still going to be able to pull this thing off. If I don't get it done by Wednesday, it's not going to happen, because after Wednesday it's going to just really start warming up. And I have to worry about the ice, the integrity of the ice. Right now the ice is still good. However, water is starting to move under it, and they're closed off the gates in the dam to start bringing the water level up for fish spawning. So we got to, I have to be careful now, because the ice is going to start losing its strength. Anyway, I'm going to take care of some more preliminaries here, a little more information, and on the next video I'm going to discuss my thermistor arrays, measuring temperatures with thermistors and lasers. There's been questions about why I don't use lasers. I've already addressed this once before on my update 3 of the Rainy Lake survey last winter, but I'm going to address it again with a little more information. I'll post a link below in that video to the part in that update 3 of last year where I discussed lasers. And hopefully if you watch that and watch the next video, you'll start to understand why lasers just are not the right tool to be measuring the curvature of the Earth or trying to determine the curvature of the Earth. And I'll go through why a theodolite and autolevel are far superior to trying to use a laser. A viewer commented in the last update the fact that I was using 3.146 miles for the distance from the theodolite on Home Island to the Franzen Island marker, and he thought the fact that I went out to 1,000th of a mile was hilarious, apparently, but it isn't, and I'll explain why. I can determine to that degree of precision, but it's really not needed, and I'll show you that it's good enough just to get to 100th of a mile to have the and be within an error bounds and uncertainty in measuring the target heights to an acceptable level. On Home Island, again, the theodolite was at these coordinates, and the Franzen Island marker is at these coordinates. You can put them into Google Earth and see, or Google Maps, Google Satellites, and see exactly where the theodolite was positioned and where the markers are on the island. So what about the uncertainty in this distance measurement? I did not cover that in the last video, and I will cover that in this. Suppose this has some amount of error in it. We'll call it epsilon. So how much error can we have in this measurement of distance from the theodolite to target before it starts becoming a problem? How much will this affect the height measurement? Remember, I have the Franzen Island target. It's on a frame. It's on the bedrock on the island, and then there were these concrete blocks And what I was doing was measuring from Home Island. I was sighting out over 3 miles away and getting the vertical angles. I have some theta 2 here, a theta 1 here, and by subtracting these, we have a delta theta as theta 2 minus theta 1, and this came out to be 3 minutes exactly. And so sighted out at 3.146 miles, this turned out to have a height value of around 14.5 feet, I believe is what the number was. And the actual height, when I went and measured the actual height, is 15.58 feet. The actual physical height measured with a steel carpenter's tape rule. So what is the discrepancy here? Well, one of the reasons for this is that there was a lot of moisture on that day I measured, and this is most likely due to compression of the image, is because the actual optical measurement is less than the actual physical. So this is telling me that there's probably some compression of the image occurring due to the fact of the atmospheric conditions. So it's not surprising at all that these two numbers weren't a little closer together, but that's not bad, really, when you think about it. In taking an angular measurement and knowing the distance to the target from the measurement position, in calculating this height, just given the angular measure and comparing it to the actual height. So that's not too bad. And when you figure out, this ends up being, if I remember on the theodolite, I have an uncertainty of 5 arc seconds that I can resolve. Well, 5 arc seconds ends up over 3.146 miles, translates to a height uncertainty of 8.2 inches. So given the atmospheric conditions I had that day, it might be possible I could have been off by 10 arc seconds, which would have, give me 16 inches of uncertainty, and we'd be well within agreement on these because of uncertainty. So when you get down near the resolution of the instrument, when you're trying to resolve angles, you can pick up a lot of error, but this really isn't all that bad considering what was occurring on that day. Now, what about the uncertainty in determining this height when there's an uncertainty in the distance measurement? Well, remember, when I'm sighting this out from a distance, we've got our theodolite here. This is our angle theta. This is our distance r out from the theodolite to the target. So the relationship here is, if this is height h, that h is equal to r theta, where r is the distance from observation to target and theta is the angular measure. Well, in this distance, I was measuring this angular difference was 3 minutes. Well, 3 minutes is 3 over 60 degrees, and if you want to translate this into radian measure, this has to be in radians. So what we do is we multiply by pi and divide by 180, and this comes out to 8.727 times 10 to the minus 4th radians. Now, so a difference or an uncertainty of the height in feet then would be an uncertainty in the distance measurement, call it delta R, also in feet, times the radian measure that we're getting in the angular differential or the angular measurement of that height. Well, theta is this number, so if I want to know the uncertainty that I can have in the distance measurement, we just solve for the uncertainty in the distance measurement, which is the uncertainty in the height divided by the theta in radians, and this works out to 1146 times delta H in feet. Now, if our uncertainty in our distance out from the theodolite to the target is 100 or 1,000th of a mile, which is 5.28 feet. 5,280 feet in a mile, so 1,000th of a mile is 5.28 feet. Then, if we solve for what the uncertainty of the height is to give us that, this works out to the uncertainty in the height in feet, or in inches, comes out to 0.055 inches, or 1/18 of an inch. So if the distance between target and observation is known to within 1,000th of a mile, or 5.28 feet, then the uncertainty that we have in the height measurement is only 1/18 of an inch. And remember, with the theodolite, we were picking up an uncertainty of 8.2 inches. So we can relax this. Let's say we relax it so that the amount of uncertainty, the additional uncertainty we're going to pick up due to an uncertainty in the distance between the target and the theodolite, let's make that 0.8 inches. 8/10 of an inch, a little less than an inch. We're willing to pick up an additional 8/10 of an inch because of uncertainty in the distance. Well, what does that work out to? Well, the uncertainty in the distance in feet is 1146 times the uncertainty of the height. Well, the uncertainty in the height is 0.8 inches. So, if we want feet, this is inches, so we need to divide by 12 inches per foot. Performing this calculation, 1146 times 0.8 divided by 12 gives us 74.6 feet. So, if we have an uncertainty of 74 feet out of 3 miles, 3.146 miles, then the uncertainty that we have in our height measurement is going to be less than an inch. It's going to be 8/10 of an inch. Well, this is certainly easily determined with a handheld GPS. To get the GPS coordinates, we don't have to go through a lot of gyrations to get a much more accurate. My handheld GPS will give me at least 30-foot accuracy. So picking up uncertainty of 30 feet on both ends for a total of 60 is within this uncertainty. So using a handheld GPS will give us less than 8/10 of an inch uncertainty in our height measurement. Well, suppose we round our height to the nearest 100th of a foot, like I've done here. I've rounded everything to the nearest 100th of a foot. So if my delta H is 0.01 feet, what does this translate into as far as delta R in feet? Well, we just put that in. Delta R in feet is 1146 for this particular measurement times 0.01 feet, or 11.46 feet. So, to have an accuracy to the hundredth of a foot on my height measurement out at 3.146 miles, I need to know my distance to within about 11.5 feet. And that's easily done using Google Maps or Google Satellite, as I did. You can zoom right in on Google satellites to see the target. You can see the tree on Home Island that the theodolite is right next to, so you can very precisely get these distances. On Saturday, April 6th, I went out on the ice with Con. We went out 3 miles just to see if we could make any measurements. It was very hazy, very humid that day, and you will see in the video to follow here that the viewing was very poor. But I was able to make a few measurements to see, using angular measurement with the theodolite, how it agrees with, say, the actual heights and lengths of the barrels. We're just a little bit past Franzen Island, and the theodolite was 39 3/8 inches above the ice. And if you recall, the barrels, the targets that we have, I have 2 columns of barrels. The bottom barrels are black. Then there's white barrels, then blue barrels, white barrels, blue barrels, and then in between the barrels I have a 20-foot sewer pipe pole in between them. It's green, and it is sticking up above the barrels by about 5 feet. The barrel stack gives me 15 feet. Each one of these is about 3 feet in height, and then what's protruding above is 5 feet. Now, I went out at 3 miles and I made these measurements with the theodolite, these vertical measurements. At the top of the pole was 90 degrees, 1 minute 15 seconds. The top of the barrels was 90 degrees, 2 minutes 15 seconds. The top of the first set of blue barrels was 90 degrees, 3 minutes 25 seconds, and the bottom of that first blue barrel was 90 degrees, 4 minutes and 0 seconds, measured with the theodolite. Now let's take a look at what this means. Well, the angular difference between these two is exactly 1 minute, or 1/60th of a degree, or 60 arc seconds. The difference between these two is 3 minutes 25 seconds less 2 minutes 15 seconds, so that works out to 1 minute 10 seconds, or 70 arc seconds. 1 minute is 60 arc seconds plus 10, 70 arc seconds. And the difference here between these two is we have 4 minutes 0 seconds, so that's the same as 3 minutes 60 seconds less 25, so that's 35 arc seconds. Now at this distance, at 3 miles, remember that the height, h, is equal to r theta. Well, in this case, r is 3 miles. And these are my thetas here, my angles. Now, let's find out how much height we get per arc second of angular measure. Once we have that, then we can multiply these angular measures by that amount to get what the differential height is in each one of these angular measures. So, for 1 arc second, remember theta has to be in radians. So, theta in radians for 1 arc second, all right, 1 arc second. An arc second is 1/360th of a degree. Then we divide by 180 degrees in pi radians. And that gives us our theta in radians. Now, we want to find out how much height we pick up with this angular measure, so we multiply by r. And our r in this case is 3.146 miles. But we want our height to be in feet. So we have 5,280 feet per mile. So this is the calculation that we make. Or, I'm sorry, we're doing 3 miles, not 3.146 miles. This is a different observation. So we have 3.00 miles. That calculation then comes out to 0.07680 feet. So what we get at 3 miles, the actual linear height measurement that we make by using an angular measure is 0.07680 feet per arc second. So we take this number and multiply by the number of arc seconds. So for this one, 60 times this gives us 4.61 feet. 70 arc seconds times 0.768 feet per arc second gives us 5.38 feet. And 35 arc seconds gives us 2.69 feet. So let's look at what we have here. Remember, the pole sticking up above the barrels is about 5 feet. We're getting optically, through an angular measurement using theodolite, 4.61 feet. We know that the barrels are 3 feet, 36 inches each. So with 2 barrels that we're measuring from here to here, we should have about 6 feet. We're getting 5.38, so we're a little bit less than what is the actual measurement. And then for this measurement here, that's 1 barrel height of 3 feet, and we're getting 2.69. So what this is telling us, again, with all the moisture in the atmosphere and the atmospheric conditions, we're probably getting a little bit of compression. This should be 5 feet. This should be 6 feet. This should be 3 feet. So in each case, we're a little bit less, and it turns out at about the same ratio. So it's telling us that we're probably having a bit of compression with the image. Now, after I did this, came back, and I went into town grocery shopping, and I found at a store that there was some really bright colored poster board. It was a fluorescent pink, and I mean it really hurts the eyes. It is so bright in natural light. So I bought a bunch of it, and in the video, at the end of the video, you'll see where I was testing it out next to the targets. So what I'll be doing is mounting one of these sheets on each of the barrels and it will help, I think, in these cloudy days to increase the contrast so that we can go ahead and make the measurements tomorrow morning. I'm really hoping that this is going to be the case, that I can wrap this thing up tomorrow and also maybe on Wednesday morning. I'd like to do 2 sets of measurements, 3 ideally, but if we can at least get 1 tomorrow, I'll be happy, and the effort will not have been wasted. Now, one other thing I'm going to do is give you all the coordinates of the proposed measurement points, so I don't have to do it in a subsequent video. So that I'll discuss next. On a previous update, I was at Home Island with the theodolite, and I measured the height of the theodolite up on this hill by the 6 mile marker target down to the ice. I had a corner reflector down on the ice, and then I also shot to a corner reflector mounted in the tree that is holding the 6 mile target. And the situation looks something like this. Here I am up on a hill. I'm shooting down to the corner reflector on the ice, and then also shooting over to a corner reflector that's mounted on this tree. There's a tree. This is a tree. And on this tree, last year I screwed in a decking screw to give me a reference point, and then mounted on this tree is this 2x4 that holds the 6 mile target. The 6 mile target looks something like this. It's almost 5 feet in length. It has 2 triangles with their apexes aimed towards one another to help find the center, and then there's the center line. Well, down on the 2x4 I have marked 180 inches to center. That is, the distance from center to that point is 180 inches, and that is on the 2x4 there. Now, the measurements I've got is that from the reference point or from the corner reflector, measured from the corner reflector to the 180 inches to center is 9 inches, 9.0 inches. And the distance between this reference mark and the 180 inch to target is 1 5/8 inches. So that gives all the relationships here that we need to precisely determine the height of the theodolite with respect to the target and with respect to the ice. Now, when I shot down to the corner reflector on the ice, the center of the corner reflector is at 6.5 inches above the ice, and this is what the theodolite gave us. Is you can go back and review that, and you'll see that this is the distance measurement. That is, a negative vertical height tells us the center of the theodolite to the center of the corner reflector is down 18.075 feet. The horizontal distance between the theodolite and the corner reflector is 177.39 feet, and then it computes the hypotenuse, the straight line distance from the theodolite to the corner reflector. And similarly here, I flipped the auto level, moved it around to shoot the corner reflector in a tree, and this is the measurements. The horizontal distance from the corner reflector to the theodolite is 12.345 feet. The height difference between these two is 1.460 feet. So that's what the theodolite gives us, and that gives me all the measurements I need there for any future calculations. Now, the coordinates for future positions for observation points on the ice are these, and I'll zoom in on this so that you can see the coordinates. I have the position we're at the barrels for these coordinates, latitude, longitude, 2 miles out, 3 miles, 4, 5, at the Canadian-US border, and then at 5.5 miles. So I'll just zoom in on that. So there's a record. So those are the measurement coordinates that I'll be using. Hopefully this will work out tomorrow morning, and I'll be making observations of how many barrels we can see at various distances from the barrels. One of the consequences of the measurements that I've made over the last few days is that I have a wonderful opportunity for monitoring and assessing the effects of refraction in an optical corridor. I have this structure over on Franzen Island, which is this channel marker, and it's mounted on this rigid aluminum structure. The members here are about around 1 inch square stock aluminum, and this structure is mounted on a concrete base that's poured on the bedrock of Franzen Island. So this thing isn't going to move. I mean, this thing is rigid. And we know that there's a ladder on this structure, that the rungs are exactly 1 foot apart. And there are cross members every 5 feet. So I have many points that I can precisionally know the values of. I know these are 5 feet. From our previous measurements here, these blocks are 16 inches. And from the top of the blocks to the bottom of the channel marker, we know this is 15.58 feet. So I can pick many points on this structure in which to sight and get angular measures, get vertical angles on this thing. And why this is going to be very good is the fact that back here on my property I have a dock. And when Jesse Kozlowski was here last year, we put a pin in that dock, and he measured using his geodetic equipment exactly what those coordinates are. And we also know that there's a pin, a geodetic pin, on Franzen Island. He measured that and has that coordinates. In fact, the U.S. government has the coordinates of that in their archives. You can go online and put in the number of this particular marker, and it'll give you all the data on this particular marker regarding latitude, longitude, where it is, relationship to U.S.-Canadian border. It's very good. So we know from the geodetic coordinates this distance R precisely. Well, within, anyway, a centimeter or two at most error. And this is roughly 2.72 miles. So what I can do now is mount my theodolite tripod here so it's centered with that pin, put my theodolite here, and shoots points on this structure. So for example, if I shoot a vertical angle there and the vertical angle here and measure the differential, that is, we get the difference between the vertical angles. Remember, the vertical angles are measured with respect to a vector that points to the center of the Earth. So we have a theta 2 and then we have a theta 1. This theta then is just vertical angle theta 2 minus theta 1. Now, this height difference, whether it be from the top of the concrete block to the bottom of the marker or points on the structure, I know these distances these lengths precisely because I've gone there and I physically measured these. So I know what these measures are physically. So all I have to do now is we use the equation H equals R theta, where theta is the angular measure between any 2 points, say A and B on the structure. So this would be theta AB, the vertical angle of A minus the vertical angle of B. I know R precisely. So H, when I've measured this vertical angle to within the 5 arcseconds capability of my theodolite, when I perform this calculation where theta is given in radians times this R that I know precisely, that H value better agree with what I measured physically. And if they don't agree, then that's telling us we have some refraction going on. If there's no refraction, the value I get for H from A to B better agree with the physical measurement. And if it doesn't, then we know there's something going on in the atmosphere between the theodolite and the structure out at 2.72 miles. So moving forward through the summer, I should be able to accumulate a lot of data under different conditions. I can measure the temperatures in this optical corridor and relate these angular measures, and later, after I accumulate enough data, analyze it to figure out what's going on with refraction. And there's probably a good opportunity here for writing a scientific paper on this, because I have a wonderful opportunity with this structure and knowing these 2 points precisely and having a precision piece of equipment like this theodolite. I can tell what's going on in the atmosphere between these structures. So it'll make for an interesting ongoing investigation. I'm out at 3 miles out from the barrel targets, a little bit past Franzen Island. Con ran the 3 miles out here. Come on, Con, good boy. You can see Franzen Island right over here, Franzen Island marker. That's about 3/10 of a mile away from where I'm at right now. I'm at the 3 mile mark away from the barrel targets. Doesn't look like it's going to be a good day. It's been melting all night. There's a lot of water on top of the ice. It's real slushy, so there's a lot of moisture in the air. Con's right in the middle of his big drinking bowl, huh, Con? Yeah, just a lot of water everywhere. The ice isn't long for this world. It won't take long now for the ice to really start deteriorating. See standing pools of water everywhere. Actually, the whole ice, surface of the ice has got about a half an inch, at least a half an inch to an inch of water on it. Anyway, we'll do a panoramic view, and we can see that indeed it really does look flat, doesn't it? We're looking back that way. That's about 6 miles to the Canadian shore, the western shore on the bay. Looking a little bit of northwest right now, panning towards the north. That's the Canadian shore. Shoreline looks nice and straight, doesn't it? Panning left to right, and that's because the earth is so big that you really can't perceive much of a curve at all when you're panning left to right in your field of view. It's just impossible to detect the curve of the Earth. You actually have to measure it. I've measured it. Jesse Kloslowski has measured it. Others have measured it. Soundly has shown it on the Lake Pontchartrain. Actually, without a reference, you just can't detect slight curves with the naked eye. Soundly over on Lake Pontchartrain has the best opportunity for illustrating that with the Pontchartrain Bridge, because that's suspended up above Lake Pontchartrain, and so you have a reference point with the bridge in which to compare the Earth. Out here, there are no reference points. If we could draw a tangent to the Earth, then eventually we'd start seeing the Earth falling away from the tangent line. It would be there'd be gaps starting to show up between the tangent line and the surface of the Earth, but we don't have anything like that out here. Just have the natural world. And there's the paper mill at International Falls. But again, I mean, the world does look flat. So you can't blame people for thinking the world is flat, because if all you had to go on was just your perceptions and your senses, you would conclude the Earth is flat. But fortunately, we have other information available to us through instrumentation, satellite photographs, high altitude video footage of the Earth, but more particularly, specifically from geodetic surveyors. We can measure the curve of the Earth. It's very slight, but it can be measured. And I've done it. I did that last winter. And this test is just to be more of a visual indication rather than anything specifically quantitative. But we'll see now if can see the barrels. Can't really see it with the camera here. I've tried. You can see there's the test setup right there. I can just barely see the barrels at the center of the screen. So I'll get the theodolite set up, and that combined with the camera will give me well over a 150 magnification, which we need to discern what's going on with the barrels. So we'll go ahead and do that now. I'll get set up. Okay, I'm set up. The theodolite is at 39 3/8 inches above the ice to the center of the graticule. I was doing some angular measurements on the barrels. The viewing isn't the best. There's so much moisture in the air, but we can kind of make things out. I'll show what I'm looking at here. Okay, you can kind of see the barrels with the camera. It's not a real good shot. You can see that the crosshairs are lined up with the top of the first blue barrel. After I made the vertical angle measurements on the barrels, I took the thermistor array and made some temperature measurements right next to the theodolite. The array was on the ice, so that the first temperature measurement was 30 centimeters or 1 foot above the ice, and then each additional point was 30 centimeters or an increment of 1 foot. And then I raised the thermistor array and obtained 3 more data points. So I have a total of 8 feet above the ice in which I've measured the temperatures. And here are the resistances of the thermistors, and here are the corresponding temperatures for those particular resistances that I measured with the digital multimeter. Now, in the next video, I'll show you how to calculate the temperature that corresponds to a particular resistance reading on the thermistor array. Here we can see that the temperature was fairly consistent over an 8-foot vertical height, unlike the other day where it was all over the map because of warm air mixing in with the cold air of the ice. That warm air was blowing in from the south land masses. The most temperature variation you see here is that we had the coldest was down by the ice at 2.36 degrees Celsius, and the warmest was here about 60 centimeters up above, 2 feet above at 3.18. So the difference here was 0.82 degrees Celsius, about 1.5 degrees Fahrenheit overall. So there wasn't that much variation. There was some fairly good mixing going on in the air yesterday, but or on Saturday. Now, Walter Bislin had asked me in a comment, how good are these measurements? These are very good temperature measurements because in the Type 44007 type thermistor, we are guaranteed that they have an interchangeability accuracy of 0.2 degrees Celsius. And with that, you can interchange any thermistor from any manufacturer, any batch, and you'll be guaranteed that temperature measurements will be within 0.2 degrees Celsius. Now, when doing that, you can use the standard coefficients that govern the equation that relates the temperature to resistance, and I'll show you that in the next video. Now, you can do better than the 0.2 degrees if you measure the coefficients for each individual thermistor like I have done, and you can get the temperature data to be within a couple hundredths of a degree Celsius. But just using the standard equations gets you within 0.2 degrees Celsius. And also the thermistors are very fast responding. I'll show you that too. I'm repairing my thermistor array. The cabling got damaged the other day. So once I finish with that, I can take it down to the pools of water that are standing on the ice, and we have a mixture of ice and water, and we're guaranteed that that will be at 0 degrees Celsius when you have a mixture of liquid water and ice. That's 0 degrees centigrade. So I'll put the array, all 5 thermistors in simultaneously, and read the resistances, and we'll see how consistent they are. And then by pulling it out and breathing on the thermistor, you'll see how quickly it can respond to the warmer air blowing on it. So I'll be doing that here in the next video. Today is Saturday, April 6, 2019. I was in town earlier today and I found some bright fluorescent pink colored poster board, and I thought that might help in establishing a good contrast, and it appears it just might. You can see that I've propped it up at the bottom barrel. Con and I have hiked out about 1/3 of a mile out onto the ice to see what it would look like. So tomorrow morning I'm going to tape a bunch of these to the barrels, and maybe I just might be able to get something done. Today the refraction was extremely bad. It was warm and a lot of moisture in the air and a lot of shimmer. So I'm just zooming in and out so I can assess what this will be like. It's little after 7 in the evening. And you see we got some crepuscular rays coming through the clouds there. Looking out over Sand Bay, looking north into Canada right now. Ice fishermen out there. That's Franzen Island. Right there, the marker will come up in the center of the screen. See the Franzen Island marker there. You can see a lot of shimmer yet on the ice. The sun is close to setting right now. Let's see what this looks like now on the computer. Now, Con, shall we go back home now? Huh? Okay. He's been a good fella today. Haven't you, Con? Let's go home, okay? Let's go. Now look at the size of Con's paws here. This is my foot. These are size 8s. That's Con's paw. Yeah, incredible. Huge paws. Let's go, Con.